Hello students, let us now begin Module 3. Module 3 and Module 4 corresponds to the Chapter 2 of our textbook, Matrices and Linear Equations. Now what is a matrix? A matrix is a rectangular array of numbers. Now in this course, when I say a number, that usually means a real number. Here I'm dealing with matrices for the first time, so I specified over R, but when I don't, it still means matrices over R. Same for the vectors, same for everything. Any number here in this course is a real number unless specified otherwise. Yes, it is possible to consider the rectangular array of, say, complex numbers, but if I do that, then I'm going to specify this is a complex matrix. Do I have an example? Okay, here's an example. A rectangular array of real numbers. Now, what is the size of this matrix? How many rows and how many columns? There are 3 rows, and then there are 5 columns. In this case, this is m rows n columns. So we usually write m by n. But everybody can count, so you don't really specify those when you have this long expression. One more. Each number inside is called a component or entry. And then in this case, what is entry 1, 3? What's 1, 3? That is first row, third column. So first row is here, and then third column. Third number from the left, that's 7. Do you see it? How about a 3, 1? Third row, so down here, and first column, first number from the left. That's negative pi in this case. What is a 2, 4? Second row, fourth column, 1, 2, 3, 4. That's -1. Do you see what those indices stand for? A, ij means ith row, jth column. Okay. Now, this expression is humongous and often cumbersome, so people use abbreviation, and this is a complete abbreviation. This expression here and that big expression are completely the same. How are they the same? We are talking about capital A equal to small a, ij, so we have 2 indices ij. But how many i's and how many j's? How many rows? There are m rows. And how many columns? There are n rows. So this is m by n specified. So you don't really have to write a11 all the way to am1 to represent the m rows and then do the same for n columns. So this big expression and this first expression are completely the same. But then again, what's the purpose of abbreviation? You just want to make it simple, right? So frequently you use the second abbreviation. In this case, I did not bother specifying the size m by n. So I'm not completely sure how many rows and how many columns in the second case. So if there's danger of confusion, of course, I'm not going to use this kind of second expression. But if there's no danger of confusion, there's no mix-up between several different sizes. In that case, I may use the second expression. Let's see, some more jargons are here. A matrix consists of rows and columns. These are rows. Horizontal array. So blue row is first row, red row is the second row, and so on and so forth. And as a matter of fact, frequently people call them row vectors because what is a vector? It's an n tuple of real numbers, and if you take the row, indeed, that's an n tuple. And that if you put in appropriate algebraic structure in there, vector addition, scalar multiplication, then it really is a vector. And indeed, we do have those kind of algebraic manipulations, so it is okay to call row vector. Actually, it is a little bit more correct to call it row vectors, but for the sake of simplicity, let us call it rows for the time being. And these are columns, vertical. For the same reason, a little bit better term will be column vectors because these are n tuple of real numbers, and then we have appropriate algebraic computations. So yeah, they're called row column vectors, and that's a little bit more precise terms, but simply frequently we may call just columns when you have a matrix ready. Another thing, please pay attention to the location of this script, location of this index. We use superscript for columns, so jth column, and we use subscript for rows, ith row. So this one is the second row that corresponds to that. And this one here is second column, which corresponds to this. I use appropriate color coding so that you can see these things. So please recognize appropriate indices here. Superscript column and subscript row. Further expression about row vector and column vector. They can be just standalone matrices. By the way, most of the time in this course, we're going to prefer to use column vector notation from this point on. It's a little bit harder to typeset, but in terms of computation, it'll turn out column vectors are a little bit more convenient for our use. In terms of geometry, they are the same because they're both n tuple of real numbers, so they correspond to a point in Rn. So geometrically, they are the same. Okay, let's go to other kind of matrices. We went through, let's see, row vectors and column vectors. Next one, zero matrix. Oh, come on, that's too simple. All zero. Square matrix. Again, that's also straightforward. Rectangular array of real numbers, but what do you mean by square? Same rows and columns. So n by n matrix is called a square matrix. Triangular matrix. Okay. They can get a little bit confusing because upper and lower. Lower triangular matrix means everything above this blue part, principal diagonal, is 0. I'm running my mouse around 0 part. And down here, the lower part, you can have all kind of numbers there. How about upper triangular, the other way around? Here, above this principal diagonal, which is highlighted in blue, we can have all kind of numbers. Down there, all zeros. Those kind of matrices are called triangular matrices. Upper triangular and lower triangular. A diagonal matrix is both upper and lower triangular. So what's left? Only the principal diagonal. Only there I have some non-zero numbers, and some of them may very well be zeros. Maybe all of them. But in any case, up there and down here, we have to have zeros. Those are diagonal matrices. Those diagonal entries, lambda 1, lambda 2, all the way to lambda n, are called eigenvalues or characteristic value. And those are going to be important in chapter 8 of this textbook. Finally, identity matrix. We have diagonal entry, or 1. That's a special type of diagonal matrix. That's called identity matrix. I'll say this is a second simplest type of matrix. The simplest, of course, is zero matrix, and this one is the second simplest. It'll turn out identity matrix works like a multiplicative identity. Zero matrix, of course, is the additive identity. Okay, section 1, extremely simple, not really worthy of a lot of class time. Let's go to the second section, which too does not really require a lot of class time, so let's breeze through this very quickly. you can have addition of two matrices simply by adding of each component. So we have two 3 by 2 matrices, two 2 by 3 matrices, blue and red. And then how do you get the addition? Simply summing them up. Pretty simple, isn't it? Here's an example that addition is undefined. We have two different sizes. So what do I add to this 4? Because there's nothing down here where my mouse is. So this kind of multiplication, this kind of addition, is undefined. Next, scalar multiplication. Just multiply a certain real number, a certain scalar, to each entry, just like you did in vectors. In this example, we have a matrix, a 3 by 2 matrix, and then I decided to multiply by 1/3, and here's the consequence. Just an example of scalar multiplication. Some algebraic rules, they all fit your common sense, so we're going to be using all those without any kind of difficulty. Associativity, additive identity, additive inverse, commutativity of addition, and so on and so forth. But how do we prove those? Well, the idea is pretty much the same as the proof we did for vectors. We had, horizontal array of real numbers. So we have to use the real number arithmetic n times. This time we have rectangular arrays, so you have to use real number arithmetic mn times. Writing down the proof can get rather tricky, as you can see here. Don't worry too much about it. I'm not going to ask you to do this. Let's look at this. So a plus b plus c, all right? I did a proof with color coding. And inside parentheses, this is a plus b. And then plus c comes later. And then we have to do a plus b first. So we simply add up each entry. And then add c later. And then if we add c, then the a plus b was done before, so we have parentheses. And then we have to add c later. And then we can apply real number arithmetic to change the location of the parentheses, b plus c first, and then you can add a later. And what is this expression? You can backtrace. You can rewrite a plus b plus c, and then a plus b plus c like this, and then we can get back to this matrix addition expression. Exactly the same idea as vectors, just longer writing. I don't think anybody will have difficulty understanding the steps, but everybody will have trouble writing. So I'm giving you the second suggestion. I'm not going to ask anybody to write this. This one I am asking everybody to write and submit as a homework. Let's see. How does it work? Instead of writing entire matrix, I'll just abbreviate it Aij. This A, capital A, is same as this expression, Aij. And then Bij and Cij. And then just work out as just real number arithmetic with additional parentheses outside to represent matrix. So that's about it. Add a plus b first, and then add b plus c first because of the real number arithmetic, and then backtrace, and that's it. So you don't really have to go through all those dots because of this abbreviation. This one I am going to ask you to write. I just want you to get appropriate proficiency on this Aij, Bij kind of expression. That's the purpose. The idea is simple. Here are some other rules. For example, commutativity. How do you prove that? The same thing. Aij equals to Aij plus Bij is equal to Bij plus Aij. The same deal. Okay, the rest is homework. Okay, one more. There's something called transpose. Now this can get a little bit tricky because now indices are changing. Over here, there was no change in indices, you see. They all stay the same as ij. No change there. But here, indices are changing from ij to ji. If you change it back, then I'm going to get back to aij. And here's an example. We have 2 by 3 matrix, and row becomes column, column becomes row. We ended up with 3 by 2 matrix. So this row became that column. Wait a minute. Let me use some color coding. Let me initialize so that I can use my color freely. So this is blue and red, and this one is blue and red. There you go. So row became column, column became row. And then now I started from here and then took the transpose again. Column became row, row became column again. And then did I come back to the original place? Yes, indeed. Yes, indeed. Because row became column. Oop, what did I do? Oh, I just... Okay, how do I fix this? Let me stop this recording and fix this and come back. Just give me a little bit more time, please. Okay, I fixed it. So as you can see, row became column, column became row, and then vice versa. Column became row, and the row became column, so that we come back to the original place. So that kind of thing is called transpose. We just demonstrated this one here. And the others, I left those as homework, so I'm not going to go too deeply into these, but they require a bit of an exercise, a little bit of flexibility because ij are changing. So please attempt those. I mean, there is an answer key right over here. They're all proofs over here. Excuse me, let me show you the first one. Without those aij kind of thing, it goes like this. A plus b, this is a, b, and then we're going to take transpose later. We did a plus b here, okay, added up each component. And then we took transpose. Look at the color. Blue row and red row and so on, green row and so on, they all became columns. And then separate those. And then what do you have? Starting from here, row became column. Here, row became column, and so on and so forth. Yes, it works out. First rule works out. But who has time to write all these in those, all those indices like those? Even worse, all the color coding. So what I want you to do is do something like this. Okay. I just showed you it was a one-liner. And that's enough because I don't want to give away too much. After all, I assigned it as homework. So transpose, preserved addition, and transpose preserves scalar multiplication. Also, double transpose, you come back to itself. So much for algebra of matrices 1. And in the next video, let's talk about matrix multiplication.